Okay, this is 5.6 practice. We're going to do these couple problems here. So question number 1 is a carbon dating, and they give us this equation to start with. And it says, suppose a mummy is discovered in which the amount of carbon-14 present is only 1/3 of what before. Okay, so we have 1/3 of A sub O is equal to A sub O and then E, and they give us this right there. Okay, divide by A sub O on both sides, those cancel out. So I'm left with this. Okay, with E, to solve that, I'm going to take the natural log of both sides. So I have natural log of 1/3 is equal to, those cancel out, so I have negative 0.00012116 t. Then to get t by itself, I'm going to divide by this. So natural log of 1/3 divided by negative 0.00012116. If you put this into Desmos, this comes up to be 9034.6. So about 9,000 years old. Okay. Number 5. Half-life of radioactive decay is 210 years. At radioactive lead, 210 is 21.7 years. So we want to find the decay model for lead 210. So what we do is we have to find that, we have to use that equation we start with. Okay, so A sub t, A of t is equal to A sub O, E to the negative kt. Okay, so we're going to use that equation here. We got to find the k factor here, right? Okay, so if we kind of think about this, it's the half-life. So if we have half the material that we started with, okay, so we start with this, we have half of that material left at 21.7 years, so the time of 21.7. So at 21.7 years we have a half-life there. To solve this, I'm going to divide by A sub O on both sides. So I have 1/2 is equal to E to the negative k, 21.7. Okay, E, so I'm going to take natural log of both sides. Natural log of 1/2 is equal to negative 21.7k. Okay. And to get k by itself, just divide by this. So we have the natural log of 1/2 divided by negative 21.7. Okay, if we put that into Desmos, we get approximately 0.0319. Okay, so our model, part A, our model is going to be A sub t is equal to A sub O, E, and I know my k now, so negative 0.0319 and t. Okay, so for part B, estimate how long it will take to get a sample of 500 grams to decay to 400 grams. Okay, so I want it to end at 400 grams, and I want it to start at 500 grams. And I want to know the time. Okay, so to solve this, I'm going to divide by the 500. So we'd have 4/5. And use the natural log of both sides, right? So we have natural log of 4/5 is equal to negative 0.0319 t. And I'm going to take them and divide. And I get just about 7. Okay, so it'd be about 7 years for it to decay from 500 to 400 grams. Part C, estimate how much of the sample of 500 grams will remain after 10 years. So how much will remain of 500 grams after 10 years? Okay, so you just put this into Desmos there, and about 363 grams. Okay, for number 8, we're working with decibels, and we have this equation here we're going to use. So it's on a log scale, and a jackhammer. So for a jackhammer, our decibels are going to equal 10 log of 31.6200000000 I sub O divided by I sub O, which those cancel. So you're really just working this out, and that comes up to be 10 log of this number is about 105 decibels. Okay, for the Harry Potter movie, we're doing 10 log of 1.995 times 10 to the 9th I sub o divided by I sub o, which those cancel, so just log of this times 10 comes out to be about 93 decibels. And at a rock concert, we have ten to the 14th I sub o divided by I sub o. Okay, those cancel. So log of 10 to the 14th times 10 gives you approximately about 140 decibels. Okay. Number 9, we're talking about earthquakes here. Okay, so part A, we're talking about the earthquake that happened in Greece, measured a 6.7 on the Richter scale. So that would be 10 to the 6.7 I sub o. And then part B, in China, there was in 2008, there was one that was an 8.0. So that would be 10 to the 8.0 I sub o. Okay, so we want to compare these two in part C. How much bigger is an 8.0 versus a 6.7? How much more intense is the shaking? So what you do, it's the log of I over I sub o, the bigger one to the smaller one. So we have 10 to the 8th divided by 10 to the 6.7. I sub o's cancel. So if we're comparing these two right here, you can think about your exponents. When you divide, you subtract. So it's about 10 to the 1.3. This is 10 to the 1.3 more, which is about 20 times more intense. Okay, so an earthquake of an 8.0 is about 20 times more intense than a 6.7. Okay, number 15, we have these chlorofluorocarbons, are gases that increase the greenhouse effect and damage the ozone layer. CFC12 is one type of it, used in refrigeration of air conditioning, foam insulation, and so forth. And they give you this chart here. So you want to put these in Desmos, put this in the table in Desmos. Go to my notes. At the end of my notes, I show you how to do this as well. You can use this equation then to find your C and your A. It says we want to use an exponential model. We want to use this. So we put this in here. Okay. Also it says to put x equals 20 to 1920. Okay, so this would be 0. When you put it in your Desmos, you put this as 0, 5, 10, 15, and 20. Okay, so when you work that out, your C comes up to be about 0.72, and the A comes out to be about 1.041. So you can see that it is exponential growth. So my equation would be y is equal to 0.72 times 1.041 raised to the x. That would be the line of best fit. And then part B, in 2013. So 2013, we would plug a 13 into the equation. Okay, and when you plug that in there, you should get about 1.21. Okay, for number 17, part A, it says it's compounded quarterly, so we're going to use this equation. And part B is continuously, so we got to use the equation with E. Okay, so part A, we have $1,000, and we wanted to know how long is it going to be in there to grow to $5,000 at a rate of 3.5%. Compounded quarterly would be 4 times per year. Okay, and we want to solve for this t right here. Okay, so first thing I would do is divide by 1,000. Okay, then we can take the log of both sides. So I'd have log of 5 is equal to the log of this whole thing. I use the power rule, I can bring this out front. So 4 times t times log of this. Okay, then to get t by itself, I just have to divide by this stuff. So I'll have log of 5, divide by the 4, and divide by this log of 1 plus 0.035 over 4. And when you work that out, it comes up to be approximately 46.2 years. Okay, for part B, it's still, we're starting with $5,000. Sorry, we want it to equal $5,000, we're starting with 1,000. 0.035t. Okay, this is compounded continuously, so first thing, divide by 1,000. Okay, when we solve the e, we're going to use a natural log. So those cancel, so just have 0.035t. And then t is equal to the natural log of 5 over 0.035, which comes out to be approximately 46 years. So it takes just a tad bit longer for compounding quarterly versus continuously. Then number 20, we want to know how long does it take for it to double. Okay, we're still quarterly and part B is continuously. So if my principal is P, my A would be 2P. Okay, we want it to double. And my rate is number 20, says 2.5%. Compounded quarterly is 4 times. And how much time is it going to take? Okay, so first thing I would do is divide by the P's. And then take the log of both sides. So log of 2 equals log of this. Okay, remember if it's raised to a power, I can use the power rule, bring that out front. And then to get t by itself, divide by these. So I have log of 2 divided by 4 and divide by the log of 1 plus 0.025 over 4. And that comes out to be about 27.8 years. Okay, so at this percent interest, 27.8 years, your money will double. Okay, so same thing here, 2p is equal to p. Where is it going to double? 2.5%. That's times there. Divide by your p, so you get p is equal to 0.025t. Take the natural log of both sides. Take the natural log of this, it's just this, and divide. And that comes up to be approximately 27.7 years. Okay, number 21 says a construction worker wants to invest $60,000. So our principal is $60,000. In a pension plan, one investment offers 7%, which is good, compounded quarterly, so 4 times per year. And the other offers 6.75%. Compounded continuously. Which investment will earn more interest in 5 years? Okay, so there's our two equations. All you gotta do is plug this into Desmos, and we'll get our answer here. Okay, typing those into Desmos, I got that amount here and that amount here. So this one is better. The higher interest rate is better, and by about $800 and 31 cents. Okay, 31 talks about basically buying a house, probably $125,000. Actually, it'd probably double that now for a house around the area, but it's over 30 years. That's what a lot of mortgages are, with an interest rate of 7.25. Interest rates now are much lower. They're probably 3.5% or something. Okay, so anyway, if we work this out here, we have $125,000 that we owe. How much do we have to pay per month, right? So it's 1 minus 1 plus. Okay, so this I right here was our interest rate, which is 0.0725, divided by how often we're paying it. So we're paying it monthly. So over 12. And we're taking that whole thing divided by the 0.0725 over 12. Okay. Okay, so this is the equation we use. We have to put that, so it's 12 per month, so it's 12 months here. But if it's for 30 years, 30 times 12 gives you 360 payments, so to the negative 360. Okay, if you plug all that in your calculator, you get your monthly payments to be $852.72. Okay, so that's part A. Now part B asks us, how much interest are you paying over those 30 years, right? Okay, so we're paying $852.72 for 360 months. We're doing that, and that gives you we're paying an amount of $306,979.20, and we only owed $125,000. Means that we paid in interest $181,979.20. So we're paying a lot more. We're paying over double in interest of what our house is, what we paid for our house. And number 46, it gives you a table. So put that into Desmos in your table, and you're going to use y1 tilde, and it's an exponential. So some number times some number raised to the x1. Okay, then you can use whatever letters there you want, but y1 and x1, and you get an equation of y is approximately 0.3525 times 1.1148 raised to the x. Okay, that's about what Desmos should give you for your equation. So an 80-year-old, okay, 80-year-old is the x value, so I'm going to put the 80 in there. So 0.3525 raised to the 80th power, and that gives you 2103 deaths per 100,000 people. Okay, and the last problem was number 48. Another one, we had put it in there. Okay, put it into Desmos. Okay, but now it tells you to use the function y1 tilde a plus b natural log of x. Okay, so now we see that it's a natural log function here. X1, don't forget the x1 there, both of those. Okay, so when you get that into Desmos, you get approximately 19.96 plus the natural log, I'm sorry, b there, b natural log of x, okay? And the b comes up to be 18.34 natural log of x. That's sloppy. Natural log of x. Okay, so there's your equation for number 48.